Hello, this is an introduction to eMEEF, an enhanced measure of mask quality. We are talking about a totally new concept of mask quality measurement. The work has been done in collaboration with our partners at Samsung and D2S. Motivation of this work is quite clear. It is commonly now known that mask errors will transition themselves onto a wafer surface. As such, they cause both local CD uniformity problems and, in general, possibly big yield issues. So in order to estimate the impact of the mask error on the wafer surface, for the last decade, people used a concept called MEEF. MEEF is basically the predicted ratio of the given mask error impact on the wafer. The common assumption, though, that has been built into MEEF, or mask error enhancement factor, that all mask shapes have the same sensitivity to the mask errors. It used to be true because most of the mask errors were due to random effects, and there is really no dependency on the shape that these random effects have been affecting. However, recently, with appearance of the small features such as assist features and generally having smaller and smaller features on the mask, such as even the main features in case of EEV, you would have a situation where different shapes would react to the same type of the mask error differently. Let me illustrate it with an example. If you look at this rectangular features on the masks, the energy deposited into the mask resist profile is changing dramatically depending on the size of the rectangle or a square. So if you look at the collection of the squares described on the slide, you will see that from the smallest to the largest, the slope or the sensitivity of the mask to all sorts of common variations due to the processing changes dramatically. It changes by about 30 to 40%. If so, we can conclude that mask error will actually depend on the mask shape. The larger shapes would have smaller errors, and smaller shapes would have larger errors. That is not built into the common MEEF function. So with that in mind, we will introduce a new concept, eMEEF. eMEEF is eBeam-driven mask error enhancement factor. What's new in eMEEF? How is that different from the common MEEF? In case of the common MEEF, as we mentioned before, mask error is considered to be purely random. Therefore, it's approximated by a simple bias. You would apply bias to the mask, and then you would use the litho simulator to obtain how much of that bias is transferring to the wafer. So the MEEF is basically just changing the CD of the mask to the change of the CD of the wafer. In case of the eMEEF, we will apply a slightly different concept. We'll be more diligent. We'll take the mask design, simulate it with an eBeam simulator to see how the energy of the eBeam will be deposited in the mask resist. And then we will consider varying that energy by some prescribed amount and seeing how that changes the mask profile. After that variation has been done and mask profiles have been obtained, we will see how those changes will affect the wafer. So the definition is different. Now let's see if changing the definition will result in a different predictions of mask error affecting the wafer. But before we go into predictions of eMEEF, let's first set some sort of a common ground between eBeam-driven MEEF and the commonly used MEEF. So in order to do it, let's normalize it in such a way that both functions, are the same for the large features. Now, why is that? This is because, as we said, for the large features, for the large mask shapes, MEEF is perfectly fine. It has been used for the last decade and it's been working quite well. It's only for the small features where the eBeam dose profile varies a lot, we will have to introduce eBeam-driven MEEF. So with that in mind, let's make sure that MEEF and eMEEF are actually the same for the large features, and that we'll use as a normalization. In this slide we go through a process where we normalize two functions. It's actually very simple. When you calculate eMEEF, just make sure that the amount of the dose variation that you apply is going to give the same result on wafer for large features as amount of CD bias that you will apply for MEEF. Okay, now that we normalized MEEF and eMEEF and we know that they are the same for the large features, let's see how they affect the smaller features. So here we take a slightly unusual example. We will take an ILT feature, which is the curvilinear mass shape. We will look at it and see how dose slope looks for that particular shape. Since this is a curvilinear feature, majority of it is made of the corners, and corners have notoriously poor eBeam dose profile. So we actually can simulate it and see that most of this shape has fairly low dose profile. So it's a good candidate for studying the differences between MEEF and eMEEF. So now that we're done with normalization and we picked a feature for us to study, let's go into details. So we'll take this curvilinear feature, actually part of it, so we can study it in much more detail. And we will perform two types of simulations. One is using the conventional MEEF approach, where we would bias the feature by prescribed amount, and we will then perform litho simulation and see how the wafer contours will look when we bias feature up and down. And the second approach is where we will take the feature, we will perform eBeam simulation with varying doses, and then see how the wafer changes. Mind you, in this process we will use normalized eBeam dose variation, meaning that we will apply such eBeam dose variation that would be equivalent to mask bias for large features. So what we see is that wafer variability is quite different. In this particular case, for the biased mask, the response on wafer is much smaller than for the eBeam varied mask. So, well, what does it mean? Perhaps it depends on the shot configuration in a sense. Maybe we chose the wrong one, but it's clear that depending on how we approach the simulation using the MEEF or eMEEF approach, the results will be quite different. Okay, so, well, that's not quite entirely unexpected, because we know that areas with a different dose slope will have a different response to the mask error. And if they have different response to the mask error, some of that mask error will transfer to the wafer. So the result is not totally unexpected. Let's explore this a little bit further, and let's try to change the shot configuration for the curvilinear feature. Initially we used a very simple horizontal slicing for it. Now we're going to try something a little bit more complicated. We will use overlap shots to deliver more dose to the corners, and we will use exactly the same number of shots, but we will apply them in a different order. That's the picture below. Now, as we can see, if we change the shot configuration and deliver more dose towards the edges of the feature, we will have much better dose profile. And we expect that with such dose profile improvement, we will also see an improvement on wafer. Indeed, if we do the simulation, and in fact we can go all the way and perform the collect the mask SEM images as well in the real experiment on quartz. But if we do the simulation, we can see that applying two different shot configuration will result in totally different wafer response. In one case, the wafer response, if we use horizontal slices, the wafer response will be much worse than predicted by MEEF. In another case, if we use the overlap shots, in this case, the results will be actually better than what predicted by MEEF. And that's a very important point. Since mask errors depend on the shot configuration chosen, because the shot configuration chosen will determine the eBeam dose slope, so will the wafer response. And therefore, using different shot configurations, you can obtain MEEF that will be either under or over predicted conventionally. As we can see, our SEM simulations also show that there is significantly more edge roughness on the mask using the non-overlap shots than it is using the overlap shots. Now, here we're using a fairly robust model of varying the eBeam dose and looking at how that affects the mask profile. That's a very good method of studying the mask error sensitivity. However, one can propose a different method, a different source of the error, which is the local source of the error, more of a Monte Carlo driven source of the error or random source of the error. That means that instead of varying dose uniformly across the mask surface, we may want to study the local dose variations, local size variations due to variations of the aperture, or short placement variations due to the stage inaccuracies. We want to see if using a different model of mask error, that is the Monte Carlo driven model, we will get a different result, meaning that we may be more in line with conventional MEEF estimation than we would be with eMEEF. And if we do it, we will see that even if we perform the totally random and totally local variation of eBeam dose, shot position and shot size, we are actually going to see very similar trends to the trends obtained by the global variation of the eBeam dose. That's very interesting. Now, as you can see that doing random Monte Carlo of shot size, shot placement, and dose gives about the same prediction. That's maybe lucky because maybe they just work for this particular feature. We want to see if this trend holds for a much larger set of features. When we study more patterns, we observe very similar effect. Trends obtained using Monte Carlo model and using the global eBeam bias, effectively eMEEF model, are the same. Trends obtained using MEEF model or constant geometrical bias are quite different. And depending on the type of the shot configuration that we chose, eMEEF can be under-predicting or over-predicting the MEEF. That's very interesting. So MEEF is basically fixed by OPC. eMEEF depends on the type of shot configuration chosen. In summary, eMEEF is a good predictor of mask errors, and therefore it's a good predictor of mask error-driven wafer CD uniformity. eMEEF is normalized to be exactly the same as MEEF for all large patterns. Therefore, it is just as good of a predictor for mask error enhancement factor for older technology nodes. But for the advanced technology nodes, anything at 20 nanometers and below, eMEEF is significantly better. eMEEF adds much more accuracy on smaller and curved patterns. Nature is more complex and its richness is much more obvious for smaller technology nodes. If in case of MEEF all we had to do is to use bias, geometrical bias, and then litho-simulate it and see what the difference ratio between changes in mask and changes in wafer, then with eMEEF you have to do a little bit more work, but you get for that you get much richer picture, much more accurate picture. With eMEEF you have to perform mask data preparation, basically obtain the shots needed to print a given mask, then perform eBeam simulation for those shots, and then perform litho simulation, and only then study the difference between mask image and the wafer image. But for that richness you get much more accurate mask error function predictor. Thank you.